What's the etiquette of talking with this on? Can I
I think you can take it
with that
off.
on?
Yeah, I think we can all take it off when we're in the room.
Right.
Okay.
Very good.
Yeah. So to everyone on Zoom, we apologize, but we had some problems. So all we can do for you is have this laptop record the speaker, and hopefully it's fine. It's recording as well, so it's the first week. Hopefully from next week on it will be a bit nicer, but it is what it is this week.
Yeah.
I apologize.
Anybody wants the PowerPoint slides afterwards, you're welcome to just email me.
Okay, so welcome everyone to the Applied and Computational Math Seminar. It's nice to see you all in the room. And it's my pleasure to introduce Professor Nico Gray from Manchester, who's a guest of Tom Barker, who's a new lecturer. And Tom, if you'd like to introduce the speaker, perhaps.
Yeah, so I guess Nico was my PhD supervisor in...
Student, I thought.
yeah, he's still my student. He's doing quite well. Professor of Applied Mathematics at Manchester, specializing in granular flow and rheology, segregation. You originally at Manchester, weren't you?
Yeah.
Your undergraduate.
Yeah.
And then moved to Germany.
Yeah, I was in Germany for a while. Yeah.
And then
Come on, give us the real dirt. You're a student.
we went on a really nice trip to Hawaii together. It was definitely justified.
Yeah, okay. Yeah. So with a slight delay, it's over to Nico, and it's 35 minutes what they go.
Okay, right. Okay, so I'll do my best to whiz through various things. So let me sort of explain a little bit about what you're looking at. You're looking at a flow down an inclined plane, and it's sand, and sand is all roughly the same size, and that's the downslope direction. And it's an interesting flow because the sides of the flow become stationary just automatically. What you've seen there is the flux as the flow has just changed. It's now a lower flux, and it's produced a channel that sort of sits inside the original channel. So you've got these levees and then levees within levees. And these flows are really quite complex because they're picking the height of flow and the width of flow and velocity profiles across them. And so this one is sort of a motivator. So I've worked a lot with geologists, and so this is a flow that's motivated by working with geologists. So, yeah. And what you'll see in a minute is we'll change the flux again, and then all this structure that you can see there is all swept away, and some even wider levees form at the sides. Here it goes, this wave comes through. And then
What's it moving on? So that's not a flat surface.
It is a flat surface, but it's structured with grains. So we just glue a load of grains on. In fact, since you've asked, I'll show you this now because I was going to show you this at the end. Normally I pass this around, so I don't know what the etiquette of passing stuff around in this COVID thing, but you could do this yourself, and you'll see flows that are like this. This is monodisperse. This has got two types of particles in it. And so all you do with this thing is you very gently incline it, and the gentler that you incline it, the better it is. And you see size segregation going on. So you see the darker particles going to the surface, oops, and then it breaks into a series of fingers. Another go at it. So you've got sort of fine spherical particles and darker, more angular particles that want to stop, and you can create a flow that's completely dry that looks as a bit like sort of wet paint dripping down a wall, and it's got these little levees on the side. And so that's what the sort of types of things some of the geologists are interested in. But here I'm trying to do it in its simplest state, so it's just monodispersed, get rid of all the size segregation. Okay, I'm not sure what the etiquette is. I will put it here, and you can either come at the end and I will let you play with it, or if the seminar organizer allows, then it can go round, but maybe it isn't a good thing. I will clean it afterwards. Yeah, yeah.
Yeah, just what the surface you say, like it's
So
what's it for? Could this be done on flat surface?
it can be done on flat surface, but what you get is you get some roller waves, some of the particles that get to the front, so they sort of start bouncing off.
Okay.
And so this just helps the particles stick.
Right.
Yeah. So I'm going to get confused with laptops. Okay. So this is one of the problems I'm going to tell you about. Not sure how much time I've got to tell you about them, but you can see the static levees form. The front comes down. Here's a sort of steady channel with a flow in it, and here's it draining out afterwards. But let me tell you a little bit the story of that. So in granular flows are sort of notoriously difficult to model, and for a long time we haven't known anything very much about the constitutive laws, apart from they were supposed to be rate independent, and there was some Coulomb type friction. And basically there was a project in France, a community project, where they looked at these things and took the Coulomb law and actually said it isn't perfectly rate independent. That would be this thing being constant, but the friction mu is a function of what they call the inertial number. And the inertial number is itself a sort of non-dimensional number formed by the shear rate, particle size, and that's divided by the square root of the pressure divided by the density. And that is the whole idea of this mu of rheology, where the friction sort of goes up like this, and sort of, for high enough inertial numbers, it sort of becomes, or it might become rate dependent. Maybe it's got some linear dependence. As this friction evolves with this inertial number, the solid volume concentration also evolves. And for quite a long region, it's fairly constant. You get over a threshold and it starts to decrease. I'm going to ignore that, so I'm just going to assume the flows are incompressible and sort of tell you where we are from that. So I'll start off with something that I actually did with Tom, and it's just to show you the equations that sort of get the heart of it. So if you go with that rheology and you assume it's incompressible, and you've got incompressibility, and then you've got an equation, a momentum equation that looks like Navier-Stokes equations, where you've got the viscosity eta, that instead of being a constant, of I, the pressure, and then it's divided by the shear rate, and that in this notation that we're using, where we're using D is the strain rate, and so this is half the shear rate. Okay, so there's strain rate, pressure, dependence sort of all going in that. And this function, traditionally in the literature, it's sort of approximated by this inertial number. And so that's where things started off. And turns out actually that rheology isn't always well posed mathematically, so that the equations can become ill posed. It's well posed for an awful lot of the time that you want it to be. But if you go to low inertial numbers or high inertial numbers, it can become ill posed. And Tom actually came up with a nice way of making it well posed for a lot of the time by slightly bending that curve. And these are some of Tom's calculations, where what we're actually trying to compute is a flow down an inclined plane. So this is all inclined, and it's a steady. It starts off as a steady uniform flow, where the pressure is essentially hydrostatic, and then there's a velocity profile given by this sort of profile. That's known as the Bagnall solution. So that's what it starts off as. But when you try and compute it, it's well posed mathematically, but it's still unstable, and so it breaks down into these ball waves that you see developing. And you actually, if you do experiments, because I'm a mathematician that does experiments.
Is that periodic?
Yeah. So I'm a mathematician that does experiments. Okay, and so these are experiments on a fairly long sort of little flume we have in the lab. It's maybe 3 meters long, and you just have a flow out the hopper onto this chute, and it just breaks down into these waves spontaneously. And this is actually biodisperse, so I'll talk to you a bit about that later on. The large particles go to the top of those flows. Those are the green ones and the white ones underneath. You see these waves coming down, and they're moving roughly at constant speed. So this is a space-time plot of that. See them coming down. And there's sort of merging events, all sorts of interesting dynamics going on. Interestingly, the waves actually travel faster than any of the particles. So whereas you might think there's some sort of green fronts moving down, it's actually the particles are sort of concertinaing as they're moving backwards relative to these waves. So particles are all going down slope, but the waves are going down slope even faster. So there's interesting dynamics going on. So what I spent most of my career doing is actually depth average modeling. And so I'm telling the story back to front because it's only recently that we've gone to non-depth average modeling. But if you take those Navier-Stokes type equations and depth average them, then you can come up with equations for the avalanche thickness and depth average velocity. And they look like this. Normally when you depth average, you chuck away most of the rheology. And so these terms over here, you normally just throw away. And those would be sort of shallow water-like equations. Where there's a source term over here with gravity driving it down the slope, or a component of gravity driving it down the slope. And then there's a basal friction that resists the motion if it's in motion. So if it's in motion, the direction of the friction is to oppose the direction of motion. And if it's stationary, then it just picks a direction that opposes the resultant forces that are left over in the momentum balance. But you can derive, using that mu of I rheology, an extra term, which is over here. And that's important for a number of things. So if you want to predict the cutoff frequency of roll waves, then we need that term. It also gives you nice sort of solutions with velocity profiles across channels, which you don't normally get. And if you're trying to do self-channelization problems, we need that extra term. So I'll tell you a little bit how we managed to derive that term. So if we just do a formal depth integration of the Navier-Stokes equations, or these ones for the mu of I rheology, then we end up with a basal friction that is actually a friction law that looks like the original mu of I friction law, except it's Froude number over H dependence on that. And this is actually partly where the mu of I law came from. So I'm really telling the story back to front. This came first, and then the mu of I rheology came afterwards. And the Froude number is defined here, so that's just the flow speed compared to the gravity wave speed. And the way I'm deriving that extra viscous term, depth average viscous term, is actually just to consider these in-plane deviatoric stresses. So I can write that down. And then I can use shallowness to sort of like pick off the leading order components of this dxx. D is the strain rate, and this is the second invariant of it. And I can use that Bagnall solution to evaluate those things, assuming that there's some sort of slow variation in the thickness of the flow. And so this is so just putting those into those formulae and just evaluating, I end up with this formula, where it's got some Z dependence, and then I can depth average it. So just depth average it. And that isn't quite what I was expecting, because I was wanting a viscous term, and I've got now gradient in the HDX. Well, I don't really want a gradient in the HDX. I really want to fit in the U bar by dx. But what I can do is depth average the Bagnall solution, and then that gives me an explicit relationship between H and U bar in that depth average world. And I just use it to convert this DHDX into U bar by dx. So it's a bit sort of ad hoc is this derivation, but that gives me the form that I want, and that's what I'm going to put in. And what it gives you for free is actually this coefficient mu. Mu isn't, it's related to the viscosity, but it's not actually viscosity. But it gives you that in terms of things that we already know from the rheology. So we don't introduce some sort of amazing sort of new parameter. This is sort of given. So it's a bit to take away from that. And so when you put all that into a sort of one-dimensional world and try and solve problems, this is what everything looks like. Viscous term in that one-dimensional world, like that. And then we can solve a sort of steady uniform flow going down the inclined plane, and here we're just perturbing the inflow sinusoidally. And you can see this growth of this train of roll waves going down the slope. And so, it's doing the right sorts of thing. And what you can do is you can calculate the spatial growth rate of the instability. And so this is a stability analysis. And if it was inviscid, so if we didn't have those viscous terms, what we'd find is the growth rate as a function of the frequency of oscillation would tend to a sort of finite limit, be unstable for all frequencies. But what actually happens in experiments is these guys actually had a loudspeaker they had their flow going down, and then they used the sound waves from the loudspeaker to sort of disturb the free surface at a given frequency, and then they could look at the growth rate of the waves. They're proper experiments. It's not a mathematician pretending to do experiments. And what they were able to do was measure the growth rate, or in fact it decays, these perturbations decay above a critical frequency, and they could measure this critical frequency as a function of the through number of various information. And the good news about this very ad hoc derivation of mine is that it picks off precisely the right through number critical frequency relationship without any fitting parameters. So somehow we're picking something up that's good. Okay, so that's one element of the model that I need. And I go back to this little world of mine where it's producing these levees. And so here you're seeing a sort of zoomed out view of what we actually see in the experiment. You can see the levees being formed and then the flow going down the channel. And we see lots of little waves on here, which I'm not picking up. I don't know what those are. To be discovered what those actually are.
Is it a sort of a stick slipping?
It's certainly eroding down and depositing. So there could be to do with where the interface is, and there could be some sort of complex interaction with the bed, but we just don't know at this point. But you can see the front coming down, everything's mobilized in the front, and then shortly behind the front, these levees are sort of kicking in. And then we've got a steady channel, and then eventually this flow drains, and then we're left with a slightly thinner flow. Ooh, you just saw it behind me, draining. So there we go. Okay, and the way, I think there might be various ways of modeling these things, but the way we've developed is sort of motivated partly by what you see in experiments, and partly from these guys, Poulican and Fortin, where they were doing these experiments, and to get their flow rule, what they had is they had an inclined plane, they had a steady uniform flow on it, and they stopped the inflow. And what they find is they get a deposit of grains on the inflow, on the slope. And they measure that thickness, and they call that H stop. And they can measure the thickness of the deposit at various angles. And that gives them something very useful that they use to derive their flow rule and their friction norm. So this was a key observation. The other key observation is when you've got this static deposit on this inclined plane, to get it to flow again, you actually have to incline it further. And so they call that angle the zeta start for a given h. And if you invert that function, you get h start as a function of the angle. And this is higher. And so you get all sorts of really complicated dynamics in this region between h start and h stop. And these observations translate into a friction norm. Well, these observations, together with careful measurements of the steady uniform flow speed at given thickness to the h stop depth, give you friction norm. Drawn it here in one particular part, in two cases actually. This is for glass beads, So this bit is the usual U of I law. This is the U of I law. It ends up as a function through number. We've just averaged it. Both of those cases. And what this observation is telling you is there's actually a static friction that's multi-valued. So the multi-valued static friction. And the minimum dynamic part of the thing where you get steady uniform flows at these 2 points. And that's lower than the maximum static friction. And so we have this monotonically decreasing bit that we don't know very much about, but we just join it with a linear, at the moment, we're just using linear functions to just join it up. We don't know very much. But even not knowing very much, we can do stuff. So we can actually compute things. Oops. Oh, yeah, this works. So these are just using that model with this non-monotonic friction law and trying to compute the levered flows. So here you're looking at velocity, on the other side you're looking at the thickness. You can see this front propagating down, and you can see the formation of these static levées on either side. Because of those viscous terms, we've got a velocity profile across the channel. And actually, if you look at the thickness over here, you can see the thickness is constant across the channel. And we get to 100 seconds and we let it drain out just to sort of do it more. You see everything solidifies. It just gets a little bit thinner in the center of the channel. How long have I got?
20 minutes.
20 minutes. Oh. I should give you a whistle. Okay, so you've got an idea that we've got something that can do levées. So and it'd be nice to figure out what would look as though we've got a steady state. And so it'd be nice to figure out the steady state, especially because it's a complicated flow that's picking its own width, and it's picking its own height, and it's picking its own velocity profile. So if I want a steady state solution, I'm going to assume that there's some width of channel and make the flow sort of one-dimensional just across, so the x coordinate goes. And then the first thing is mass balance just reduces to this. And from that, the boundary condition on the sides, so there's no velocity across the sides, tells me that the cross slope velocity is 0 everywhere. And if that's true, then my depth average cross slope momentum balance just reduces to this pressure gradient, the depth average pressure gradient 0. And I can solve that, and I just get a constant thickness across the channel. Don't know what it is, but it's constant. And then my final equation is my depth average downslope momentum balance, and that gives me a sort of second order equation across the channel, where H is now something, I don't know what it is, but it goes in there and it's constant, and I have to solve it with that friction law. And these leveed flows are really quite clever because they pick this interface. So it's determining this interface, and at this interface, the velocity is 0 and the shear stress is 0 at this interface. So that's equivalent to those two conditions, and we'll make it sort of symmetric, so it's on either side of the channel. I'm putting different fluxes down these channels, so there's an integral constraint across the channel where we just integrate across the velocity profile times the thickness, and that's going to determine us the flux. And you can actually solve those problems, which are sort of free boundary value problem. You can get an awful long way analytically. It's simple enough. You can almost get a solution out of it, and you can start sort of. Actually, what we do is we sort of pick a thickness, and then we solve the velocity equation. So here's the velocity solutions, and then afterwards we can figure out where they sort of come and hit the boundary, and then that gives us the width. And then we can figure out after that what the flux was, and then we can invert it all and say, oh, we knew what flux we wanted, and then pick one of those solutions. And we can also sort of do some sort of partial reconstruction using assumed velocity profiles. So we can sort of almost do a section across one of these things, and with an assumed velocity profile, which we might assume is back null, for instance, and reconstruct the vertical structure that might see in one of these flows. Okay. And so then if you take all of those results and you plot them, what you find is that as you increase the flux, the thickness remains roughly constant, apart from when you go to low fluxes. It shoots up. And this is the width of the thing. As we increase the flux, it gets wider, but it doesn't get any thicker. And these points that you can see are some existing experimental stuff that's in the literature. They measured the width of these channels as a function of the flux. And so with this very simple sort of model, we come up with a pretty good prediction for what's going on. Interestingly, is what happens at low fluxes. So this is the same deposit mechanism. So we actually just have a funnel and grains drop onto the plane. And the flows don't flow in a nice steady state anymore. They become unstable. And these flows are very interesting. You've got little piles, pile collapses and it flows. But as soon as it goes onto that substrate, it stops. And it builds up again. And it can flow where there's grains, but as soon as it comes off the sort of erodible bit, it stops. And if we solve the equations in that same sort of situation, we also start getting pulsating flows that are no longer steady, where these dark blue bits in here are stationary, and it starts sort of building up near the source and then shedding waves off. We don't quite predict the right frequency of these waves, partly because I think it becomes non-shallow near this piling up process, so maybe can't do that properly. But these waves that start to form, they also are very mobile where there's an erodible layer. But as soon as they come off the erodible layer and get onto the underlying substrate, they deposit. So we call these things erosion deposition waves. And you see it's sort of periodically advancing the flow rates. So it's not quite, I don't know, I think it's quite a sort of unusual sort of thing. And I sort of quite like it because I can sort of look at that and say, yeah, we'll see sort of stuff like that in the field. So this is in Switzerland, in a place called Fui, which is spelled fully. And they had a pipe burst, and then it produced a debris flow. I mean, it probably looks better to you than it does to me up close, but you see it's sort of depositing grains, and then there's a wave that's going, and then it will advance this front a bit further, and then it will stop again. And then you'll see, in this particular image, you can see one of these waves static, one of these waves, and then another one coming around the corner. And each one of these is like this very small scale experiment where it's sort of advancing things down. So this is what I spend a lot of my time worrying about, really, or thinking about, sort of debris flows in nature. So this has actually got water in, and it's complicated, loads of sizes, and maybe some sort of clays and things like that. So making it a much more complicated beast, but it's still got some similarities with just a dry sand flow on a erodible soil. How long have I got? 15 minutes. Okay, you can have a look at this again. So I think this is fabulous and sort of very interesting. So it's destroying the local vineyards, but yeah, so it's a great thing. Okay, and these erodible sort of flows, I thought, oh, those are quite interesting things. And so what we started doing was some erodible experiments, where now we've prepared, so we've got the base that you see in that little experiment, and then we've prepared what we call an H-stop layer, so by letting something go down that layer and then produce a deposit, that's the deposit. And then what we're going to do is we're going to have a little cap that we've got the same sized sand in, and we're just going to release little volumes. And let me just say, normally, when I do an experiment, basically I'm doing avalanche experiments, sort of I release things, and I make a release, and the stuff goes down an inclined plane, and it comes to rest at the bottom. And the stuff that I release at the top is the stuff that I produce at the bottom. And these experiments sort of call that whole question into doubt in real geophysical systems. So this will release, and all this yellow sand starts getting deposited as it's going away, because these waves are eroding and depositing as they're moving. You see a small release here, so it's not as much yellow. So it completely deposits all the yellow, and yet the wave is moving down the slope. And it's moving down the slope completely steady. This stuff, if there wasn't this erodible layer there, it would all just stop. It would just sort of form a little, collapse a little bit, form a pile. But this can apparently, conferring mobility to this thing by having this erodible layer. Next video should play. And so we can actually simulate those things. So using those same equations for the flow, we can actually start putting traces into the flow and tracking the yellow particles and watching them deposit in the flow. So we see these things depositing. Right. So one of my escapades with the geologists was we went off to a thing called the United States Geological Survey debris flow flume in Oregon. And this is actually what got me into levees in the first place. So this is sort of where it started. And so we're chucking these sort of mixtures. It's sort of basically had a concrete mixture come and sort of, well, they brought loads of sand and stuff, the stuff that you use for concrete. And we put it all in the thing at the top, where you see some flimsy little doors. Those flimsy little doors are sort of steel things that are about that thick, and then they sort of open up. You get this mixture of, it's all wet, these flows, so it's like a debris flow. And it lets this flow come down. And you can see it sort of as it comes down, it gets a bit darker as it goes to the front of it comes down here. And as it comes out onto this run-out pan, you drop some traces onto the top of the flow, and you can see where those traces go. And you see these static levees forming in these flows. Just go back. Unfortunately, present mode, so it doesn't. I can't get that. None of them playing that. Well, this one's playing. This will tell me enough. Okay, so what you can see is this thing runs out onto the run-out panel as we're dropping those traces on, and some of them are going into the sides. So this is tracking with the flow front. Okay. We've got something that's almost like a steadily propagating wave. So traveling wave solution. Some of those are going to the sides, and then they've stopped in the real world, but moving back into traveling terrain. And some of them get rolled and lost to sight. But the sides of this thing are actually ending up darker, and that's because large particles have been dumped on the top of these levees. The picture is actually really quite complicated. Okay. And so this is this little experiment that was sort of made a slight motion around the room, but not very far. But welcome to the pit afterwards. I'll clean it afterwards.
You tip the roof.
And so this is what you should see. And so it's just a mixture, two different grain sizes. The dark ones are larger and rougher, and the fine ones are sort of spherical and smaller. And then that produces you these leveed flows. Each one of these fingers, I call them fingers, has got little levees on them. And in fact, if you don't have the size segregation and this roughness difference, you don't get it to finger. So it doesn't. And there's all sorts of really complicated dynamics going on. So the head-on view, you see this thing coming towards you. And you can see the levee sort of kicking in, and it's really rich in large particles. And then some sort of waning of the flow, and as it wanes inwards, you can see the sides are almost pure spherical particles. And you can actually see a wave that comes down and strands particles. So there's a sort of deposition wave that's coming down that's leaving an H stop there. So you'll see a transition between material that's stopped. And that's a deposition wave that's moving down this flow. It's stranding particles. There's loads of dynamics in that. So one of the things that that if you want to try and model those flows, you need to worry about size segregation. And I could talk to you for an hour on size segregation. I will do it in one slide, or try to. And so I spent a long time worrying about size segregation, models of size segregation. And essentially what you see is large particles rising to the top of sheared flows. And this is a little shear box experiment. So the walls of the shear box are sheared this way and that way. And what you're actually looking at is a flow. It's got a fluid in it, and the fluid is refractive index matched with the particles. So you can then put a little bit of rhodamine in the fluid, and then shine a laser sheet through it, and then you can get cross sections. So you can actually see through this fluid, and you can see the rhodamine sort of fluoresces, and you can then see the outlines of the particles, cross sections of the particles, and you can just shoot this sort of, or transverse this laser beam across your cell, which is apparently transparent, but it's got particles and fluid. And then just take pictures. And you get a series of pictures from which you can reconstruct the particle positions. And we're only actually doing it when these sidewalls are going vertical. So you're just sort of strobing it in this vertical position. So we start with large particles at the bottom, small particles at the top. The large particles want to go to the top, so they reverse.
Is this related to the Brazil?
Yes, Brazil nut tends to be shaken. These ones are for sheared flows. And there are loads and loads of sheared flows, lots of industrial things where they've got problems with stuff shearing, and then it sort of like segregates their particles, and you get all sorts of unexpected particle size distributions. So this is a very simple one. So from this data, we can extract this. This is a sort of space-time plot of the concentration. And we see the large ones start at the bottom and look at the top, small ones start at the top and look at the bottom. And some very simple theories can actually give you that structure. So it's just a sort of an advection diffusion, and then in quotes segregation equation. This is a diffusion, this advection by the bulk flow. This is the segregation. And it's got this interesting quadratic term where it shuts off the segregation when the concentration of fines is 0, or the concentrations of large is 0, which means the concentration of fines is 1 minus. So when phi s is equivalent. So when phi s, the concentration of smalls is 0 or 1, segregation shuts off. It segregates the particles. Okay, so what we like to be able to do is something like this, the schematic diagram that's going on in those flows, is we're segregating particles to the top of the flow, and then there's a velocity profile, and the velocity is largest at the top, so it preferentially transports large grains that are up there to the front. And then there's some really complicated thing where some of the particles, large particles, get overrolled, but they're overrolled by finer grain material, so they can segregate back up again. And so they can start recirculating. And in fact, the flow field is pushing the things out to the side. So they start recirculating and then get pushed into the margins of the levee in a very complicated process. And that's the sort of thing that we'd like to model. It's fun. It's good. I'm there. I'm on top of it. Okay, and so here's the schematic. Again, I'm going to come up with a depth average model that can just skate over all the detail and sort of capture something that's useful. So just going back to sort of like two-dimensional world. So I've got some sort of velocity profile. I've got some, I'm going to do it for sharp size segregation. So I'm going to ignore the diffusion. So I've got large over small. And there's going to be an interface on beta, and then the thickness of the flow is this. And that's going to be the sort of schematic picture I've got. And then what I'm going to do is I'm going to depth average my segregation equation. And if I do that formally, I end up with this very apparently simple equation. It just looks like another mass balance equation, which it is. It's just the mass balance of the fine particles. Here, no phi bar is the depth average concentration. And these overbar things are just the vertical averages of things, which in general I don't know very much about. But if I assume this sharply segregated structure, I can calculate this first integral. I just find that this h phi bar is just this interface on beta. And then I can calculate this if I make an assumption about the velocity profile. And what I'm going to do is I'm going to assume that it's just got a linear shear profile. And if I assume it's got a linear shear profile, then I can integrate that up as well. And so when I depth average that equation, I end up with this equation, which looks a bit strange, but actually if you make a substitution, so I make the substitution that eta is h times phi bar, I end up with an equation like this, which has got this phi bar 1 minus phi bar structure, which you sort of had in the original segregation equation. And there, that mainly occurs in the z direction, normally with things in the z direction. And so we have the phi 1 minus phi, and that's segregated stuff vertically. This one, it's got the same phi 1 minus phi bar. So it's segregating stuff, but it's doing it laterally. And so if we look at the little sort of cross-section, it's a sort of reconstructed cross-section, what you'd see is it's actually, so we already know it's large on top of small, so these brown things are large things. They get sheared to the front, and then once they get to the front, they don't just shear over and go back like this, they start accumulating in front. So the larger ones are essentially getting segregated to the front, and the small ones are getting segregated to the back.
Is it because of British condition, or would this always eventually?
If there's some large particles coming in, that's where they're going to go. That's where they're going to go to the top. And so what you can then do is take, so the first and third equations, the equations you've already seen. This one is the one that's just derived, depth averaged large particle, depth averaged large particle transport equation. And then we've got source terms again, and these are going to be slightly simpler. So I'm not putting this, what we call the hysteretic non-monotonic friction in, not yet anyway. Do something slightly different. We'll just say that this basal friction is larger for the large particles than it is for the small particles. And we'll volume fraction weight it. So depending on what's there, you'll have more or less of the large or small friction, depending on the volume fractions. So again, it's quite a simple system, and you go solve it. And so what you very quickly want to look at is this one. You get the large ones accumulating up front in a depth average sense, and they're more resistive to motion. So this front is feeling more and more resistance as they collect them, and then it starts breaking down into fingers. And that's why you get the fingers in that experiment. And this, as opposed to that experiment, here we've got continuous flow towards the front. There it runs out of stuff, and that's why you see the individual fingers that sort of can move, sort of detach from each other, and you get gaps between the fingers. Here you're not getting gaps because we've got this flow coming in the back. And that's actually what we see in experiments. So the top is up front, it's monodispersed, and it's just moving down. And this is one of these things that sustain and keep them feeding the stuff. And so we don't get the thing breaking into complete figures, but it's starting to break up into these sort of like cat's paws or something like that. And well, this is sort of part of the motivation, pyroclastic flows down at the base of those things. You get these dense currents like these little avalanches. So these things might be 5 meters across or something like that. And they've got levees on them, and they're breaking into all sorts of really complicated structures. So go off in the field and sit on terms of one of the levee walls. So, my PhD students, postdoc, is sitting on, and this is a mountain hand. And so, you know, it's sort of interesting seeing these things in the real world at a much bigger scale. Right, I'm done.
Okay, well, thank you. We have 2 minutes for questions, and we have to leave the room just so that there's a 10-minute break before this next session in this room. So any questions to Nico?
So Nico, very early on, you shared some models that very